Welcome to the presentation by Group Smart Minings from Faculty of Engineering, University of Moratuwa. By the end of this video, you will get idea about our design project, operational monitoring and blind spot detection in drum trucks with blasting pre-work digitalization at Aruwakkalu Quarry. This is the content of this video. Now let me give you a brief introduction about our design project. The Aruwakkalu Quarry in Sri Lanka plays a major role in supplying raw material for cement production and other industrial uses. However, like many large-scale mining operations, it faces challenges related to safety and operational efficiency. Our project focuses on three main solutions to address these challenges. Those are blind spot detection in dump trucks to minimize accidents, real-time GPS-based operational monitoring to track drum truck movements and performance, and finally, digitalization of pre-blasting activities to enhance coordination and reduce human error. By integrating Internet of Things or IoT-based technologies such as ultrasonic sensors, PIR sensors, and GPS modules with a cloud-connected data system, our Smart Mine X solution provides a modern, efficient, and affordable approach to improving mine safety and productivity. Before developing our system, we analyzed key issues in current operation at the Aruwakkalu Quarry. First, in operational monitoring, existing system failed to accurately track drum truck speed, location, and cycle times. The quarry currently relies on speed signboards and VHF radio communication for coordination. However, these tools are prone to signal loss, inaccurate timing, and heavy human dependence, making them unreliable. Second, in blind spot detection, drivers experience limited visibility only around 3 to 4 meters, especially under dusty or low light conditions. Traditional safety practices such as mirrors, horns, or luminous flags are insufficient to prevent accidents, particularly when smaller vehicles or personnel are nearby. Third, during pre-blasting operations, record keeping and calculation are still performed manually using paper-based forms. Manual handling of GI forms, explosive records, and drill patterns reduces traceability and increases human error. In summary, the three main problems we identified are lack of accurate real-time operational monitoring, limited driver visibility leading to potential accidents, and manual inefficient pre-blasting documentation. These challenges form the foundation of our design objectives. To solve these problems, we developed three integrated systems. First, a blind spot detection system using PIR and ultrasonic sensors connected to an ESP32 microcontroller. This system detects obstacles or movements around the dump truck and alerts the driver in real time. Second, a GPS-based operational monitoring system that tracks each truck's speed, location, and cycle time continuously. The data is transmitted through Wi-Fi to a cloud platform where supervisors can monitor live performance. And third, a mobile application for pre-blasting digitalization which replaces manual forms with a digital interface for document handling, explosive inventory management, and blasting pattern planning. Together, these three modules create a complete smart mining solution. The equipment and methodology section explains the practical implementation of the design. This part focuses on how each subsystem was developed and hardware and software component used and how they were integrated to achieve the overall system functionality. The blind spot detection system was developed and tested using a small-scale prototype model to demonstrate the core functionality of the design. Although this version was implemented on a prototype setup, it has been carefully designed so that the same concept can be scaled up and installed on real dump trucks operating in the quarry environments. The system is based on an ESP32 microcontroller which functions as the central processing unit. It integrates ultrasonic sensors and passive infrared sensors or PIR to detect nearby obstacles and human movements around the vehicle. When an object or person enters the detection range, the sensor sends signals to the microcontroller, which then activates LED indicators and an audible buzzer to alert the operator of potential hazards. This immediate alert mechanism enhances situational awareness and provides an added layer of safety for vehicle operation. The entire setup operates on a 5-volt portable power supply, making it suitable for prototype testing and future integration into full-scale equipment. By combining low-cost components with efficient programming through the Arduino IDE, the prototype successfully demonstrated the feasibility of the concept, providing a practical and scalable approach for improving dump truck safety in real quarry operations. Next, we will demonstrate the working prototype of the blind spot detection system developed in this design project. You can see in this prototype truck, an ultrasonic sensor and a PIR sensor have been installed to detect nearby objects as well as human or animal motion around the truck. As the prototype truck moves closer to the barricaded area, the system automatically triggers a beep sound alert and LED indication warning the operator of an obstacle in the detection range. You can also observe how the prototype effectively identifies motion around the truck, demonstrating the intended functionality of the blind spot detection system. For real-time operational monitoring, we used an ESP32 microcontroller, a GPS module, a 5-voltage power supply unit, and web application for data visualization. The GPS tracker is installed on the drum truck and continuously collects data such as location, speed, and travel time. This data is sent to the ESP32, which processes and transmits it via Wi-Fi to a cloud database. A web application then retrieves this data and displays live information about the truck's current position, speed, and cycle time. Engineers can monitor truck performance in real time, analyze cycle times, and identify delays or inefficiencies in haulage operations. These systems not only improves productivity and fleet management but also enhances safety by ensuring that vehicles operate within defined limits. Next, we will demonstrate the real-time operational monitoring system developed in this design project. In this demonstration, a screen recording of the web application is used to show how the system tracks dump truck movements in real time. The application displays the location and speed of the truck on the map interface, which updates continuously as the vehicle moves. This demonstrates how the GPS-based monitoring module provides accurate live data that can be accessed remotely through the web platform. The third subsystem focuses on the digital transformation of pre-blasting activities. Using Android Studio and Firebase Cloud, we developed a mobile application that replaces manual documentation with a modern digital interface. The application supports several critical tasks like preparing digital GI forms, managing explosive inventories, designing blast patterns, and checking resistivity before blasting. It also includes offline data storage, which allows mining engineers to continue their work in areas without network connectivity. Once the connection is restored, the system automatically synchronizes data with the cloud. This ensures data accuracy, eliminates the need for paperwork, and provides complete traceability of pre-blasting records. By combining mobility and cloud integration, the application improves both operational speed and accountability. Now, let's take a closer look at the pre-blasting design Android application, which forms the third subsystem of our design project. This is the main interface of the application. It provides the user with direct access to all major features including explosive inventory tracking, resistivity calculations, GI form preparation, and drill hole pattern design. The layout is designed for simplicity and usability, allowing quarry engineers to navigate quickly during field operations. This screen displays the explosive storage checklist, which records the details of the available explosive materials. It enables accurate tracking of inventory levels, usage history, and safety checks before each blasting operation. This feature replaces manual record keeping and ensures accountability in explosive management. The resistivity calculation interface assists engineers in verifying the safety conditions of the blast area. Users can enter measured data and the system automatically calculates resistivity values. This helps to ensure that all blasting sites meet the required safety standards before proceeding. This part of the application allows authorized quarry engineers to request and obtain access for creating GI forms and managing blast data. By introducing this controlled access system, the app maintains data integrity and restricts operations to qualified personnel only. Here we can see the drill hole pattern design interface. Engineers can design and record blast hole layouts digitally, including hole spacing, depth and sequence. This feature improves the precision and repeatability of the blast designing, eliminating the need for manual sketches or calculations. This screen captures the blasting location details, allowing personnel to record the exact area where blasting will occur. The data are linked with the GI form and stored in the cloud for traceability and future reference. Finally, this screen shows the GI form generation module. Once all required data are entered, including explosive quantities, drill hole information, and site details, the application automatically generates a complete GI form. This eliminates paperwork, reduces human error, and accelerates approval and documentation processes. Finally, this screen shows the GI form generation module. Once all required data are entered, including explosive quantities, drill hole information, and site details, the application automatically generates a complete GI form. This eliminates paperwork, reduces human error, and accelerates approval and documentation processes. While the current prototype successfully met all design objectives, there are several areas identified for future improvements. First, we plan to replace the basic ultrasonic and PIR sensors with industrial-grade radar sensors to improve accuracy and durability under extreme quarry conditions. Second, the GPS tracking system can be enhanced using LoRa communication modules, which will provide long-range wireless coverage along hauling roads. This will enable continuous real-time monitoring even in areas with poor Wi-Fi connectivity. Third, we intended to integrate the GPS tracking system directly into the pre-blasting mobile application, creating a single unified platform that connects truck movement, blasting zone mapping, and worker coordination in real time. Although these upgrades were beyond the current budget, they represent a clear path toward large-scale operational deployment in future quarry operations. To conclude, our design project demonstrates how IoT-based technology can be effectively applied to real mining challenges. By combining blind spot detection, real-time GPS monitoring, and digitalized pre-blasting application, we have created a comprehensive safety and monitoring solution suitable for both large and medium-scale quarry operations. The system enhances visibility, accountability, and operational control while remaining cost-effective and adaptable to local conditions. This concludes our design project presentation. We appreciate your attention and the time taken to review our work. Thank you.